actually kind of slowed down just now. Well, Randy, do you want to?
Are you going to hit record first, or should I just do this and then you record?
I am recording.
It's already recording.
recording.
All of our chit chat here is.
Well, we didn't forget this time. Yay.
I'll just, it's set to go automatically, but sometimes I pause it just in case, but.
Sure, I can start. I wanted to say hi, everyone. Thanks for joining us tonight. I've got a super special meeting that I'm really looking forward to with Mel. Our membership is at about 61% now. We're still a little bit low. People are still trickling in, which is kind of normal, but for those of you or anyone here who hasn't paid your dues, they're certainly welcome, and I'll send you a receipt, email receipt after I get your dues, and that way you'll know I got them and everything's processed. Want to welcome a couple new members. We have a gentleman that came all the way from Albany, I think, last meeting. Afi Mock, I think is his name. I don't see him on here. I did tell him about Heart of the Valley Club too. And we have a couple, Rob and Alyssa Nance. And those are new members. And I also wanted to mention that we still have lots of glow-in-the-dark stickers with our new club logo on it and the solar shades. And also, if you weren't here or weren't at the last meeting or didn't read the IO, the board did vote to send $500 to the science factory. There's the logo, and thanks, Jerry. And we donated $500 to the science factory, which was mentioned at the last meeting, but it's worth mentioning again. And I'm done. Thank you. Oh, one more thing. Did anyone see meteors last night?
Totally sucked in here.
We watched a movie last night. It was in the fog here, and when the movie was over, I went outside and there was a sucker hole, so I grabbed all my down and my my lounger, and I was out there for about 15 minutes, and I saw 5 pretty nice ones, and then the fog socked in. So, but I felt blessed to see them. They were fast and nice.
Yeah. I saw one not quite fireball, but I saw one really bright one up in the snow at Eagles Ridge.
And you're hardcore, dude.
3 small ones. Well, I drive from West Eugene, and so I didn't want to come all the way up to Eagles Rest and then, sit on my hands. And so I just went ahead I went further up. But
that road up to the ridge is tough without snow.
It was fun. Jerry and I have been up there in some snow a few times. So
Dan, tell everybody what you saw on the way down.
Oh, on the way down, I saw a wolf. So on that road, right by the amphitheater, the same place that I saw a black bear earlier in the summer. I'll send it out to the group. I've got about 30 seconds of video of a young timber wolf just standing there in the road looking at me, and then he turns and he just nonchalantly trots down the road.
Not a coyote.
Not a coyote.
Not a coyote.
Not a coyote.
Yeah, that wolf looked terrified of you. I'm telling you.
He would have been interested if I'd had food, but he didn't care about me being there at all. He would just looked at me and then walked the other way.
It makes me wonder more and more what kind of bullet I dodged a couple of summers ago.
Yeah. I think we gotta rename the amphitheater to the Game Trail. I'm pretty sure.
Right, because there was a cougar sighting there about a month ago too.
That's right. Yeah.
I saw the lion.
Well, I saw the mountain lion.
The Eagles Rest Amphitheater and Petting Zoo.
Yeah, more like the
Meow.
Yeah.
Anyway, that's it for me.
Well, Cheryl/Andy.
Oh, there's a whole bunch of questions that people are going to ask about that. So the group up in Salem probably wonders why I referred to myself as the former first lady of the Northern Arizona University Astronomical Society too. Cheryl was the president. But I'm going to go ahead and should I stop the video to share screen or?
No, I mean, not unless you have like really bad internet.
Okay. Well,
or like
that's
20 people all share all
thing.
Online.
Okay. Can everybody
Perfect.
see that?
Yep.
Okay, so back in the EO last month, I guess it was this month, introduced the constellation Cetus. And since we're looking at doing something from the membership every meeting, a couple of minutes at the beginning of the meeting about something relevant in the sky or something relevant to current astronomical events or something of that nature. And we're hoping to get new people involved in presenting. I thought we would kick off this idea by me basically going over what was in that article that I wrote, in part because it was kind of already written, but I didn't get a chance to introduce a lot of the stuff in great depth, so including with pictures. So we're going to go ahead and do that. And one of the things that I mentioned in the article is that throughout the ages, the constellation Cetus has been drawn a whole bunch of different ways. And you can tell pretty much here a lot of the different ways that it's been illustrated on star charts over the years, and a lot of the ways it's been visualized by astronomers. And I like the fact that the older ones here are facing the opposite way from the way the current illustrations are done. I'm particularly fond of the H.A. Ray little smiley whale here versus this monstrosity that's just above it. But even on modern star charts, like these two in the center, there are no real complete agreements about how to draw it. These two are actually pretty similar, but Cetus is literally all over the map in terms of the way it's depicted. But before I got into that, I wanted to go over something very quickly that I talk about in this and basically every one of these columns, and that's a discussion of angular measurement. Really important when you're doing visual astronomy, to know how to judge distances and to be able to tell how big things are when you see them. That part's not the important part, but being able to understand it is the important part. And of course, when you think of the sky, we're surrounded by 360 degrees of it, of which we can see about 180 degrees from our location wherever we are, from horizon through zenith to horizon. And of course, the hills and things take away a few of those, but we divide the sky as we see it into 180 degrees, 90 degrees from horizon to zenith, and each degree is broken up into 60 arc minutes, and each arc minute is broken up into 60 arc seconds, as you would expect, minutes and seconds. So that's 3,600 arc seconds per degree. And that's a very, very, very small measurement. But when we think of degrees, we can use our hands against the sky, as this illustration shows, as a means of kind of determining the distance between two things, or the span of a section of sky, with an individual finger being about a degree, the full moon being about a half a degree. So if the full moon fills the eyepiece of your telescope, that eyepiece is giving you a 30 arc minute, half a degree field of view. And then, as the illustration shows, we can go all the way up 25 degrees from the end of the Big Dipper's handle to the end of its bowl, and making our little astronomy gang signs there as a means of depicting distances on the sky. So when you all read the articles, I'm sure everybody here has them memorized within about 5 minutes of reading them. I talk about angular measurements all the time, and this is just a very basic illustration of what that means. But to get into Cetus, right about now in the middle of December at about 8 o'clock, this is where we see the constellation Cetus as depicted by Stellarium. And you can see it looking again like an old school monster right in the middle of the screen, right along the meridian, that line that divides divides east from west, that runs north to overhead to due south. So at about 8 o'clock, Cetus is right on the meridian. That's the best time to observe these objects. And the first object, oh, you got one more. This is how it's depicted in Sky Safari, a little less crowded. But again, showing that old school monster style. I much prefer the smiley whale, actually. A modern star chart here. We have all of our objects for the month listed. And we're going to start with a naked eye object that's variable stars aren't really everybody's cup of tea, but it's interesting to track Mira Omicron Ceti because it does disappear completely from view. And when it's at its maximum brightness, it's a naked eye star. Even from, I suspect from the reservoir, it would still be a naked eye star. Magnitude, I think 2.9 at brightest. So tracking its disappearances and appearances over the course of a few years can be an interesting naked eye observation to make. And an image of Mira within its star field, and kind of the little graphic in the upper left illustrates the variability of Mira, that it's actually brighter when it is at its smallest. This is a pulsating star, so it actually does expand and contract. And when it is at its smallest is when it is at its brightest. And if you're following along with Mira, you can contribute to the science on it by contributing your estimates of its brightness to the American Association of Variable Star Observers. And this is its track over the course of a couple of years earlier in the previous decade. So it rises very abruptly and falls in brightness quite a bit more slowly than that. And going along to 2-inch objects for a 2-inch telescope, rather, and binoculars, because they happen to be right next to each other. Actually, I think this is for binoculars and a 4-inch telescope. We have M77 and NGC 1055. M77 here at the bottom being one of the frequently said to be one of the fainter of the Messier objects. I think that's crazy. I think it's actually quite a bit brighter than it's given credit for. Visible in a pair of binoculars pretty easily near the star at the base of the whale's tail. So here's the tail, the fluke up here. And if you look at Delta Ceti right here, this chart actually has the two of them reversed. This is M77 down here, and this is NGC 1055 here. But you can see NGC 1055 up here looking like the smile on a very celestial happy face, or bemused face maybe. But NGC 1055 visible in a 4-inch telescope. You'll need about an 8-inch telescope to see this lovely dark lane that crosses it. At least an 8, probably a 10-inch. And with binoculars and small telescopes, you'll just see the middle bright portion of M77. And proceeding to an object for 4-inch telescopes. And if you think you can't look at galaxies with small telescopes, that's, don't limit yourself based on your optics. Always assume that you can see something until you can't. And this is a lovely face-on spiral galaxy that in larger telescopes shows its spiral arms relatively easily. It's unfortunately a little bit low in the sky for us to make the structure out as easily. So you'll need a little bit larger telescope than you would if we were living in Arizona. But the spiral structure in this galaxy is visible in a 12-inch scope under good conditions. And the galaxy itself will show rather easily in a 4-inch. And our object, I'm doing these always in 2-inch increments, which is probably overkill, but I like putting a lot of objects in here. So we're finding stuff with every aperture size. And here we're going to look at something that's not a galaxy in the middle of this little jellyfish-like pattern over here, as I call it. And this is the planetary nebula NGC 246. And often called the Skull Nebula, not just because of its appearance, but also because it becomes visible relatively early in the evening, even around the end of October for Halloween. So we get our lovely skull-like nebula, and it does show these little traces and wisps within it. This is a sketch that I made a long time ago of it that shows how it looks in a 12.5-inch telescope. A large, bright planetary nebula, good for a 6-inch or larger telescope. And when I mention, oh, this is an object for a 6-inch telescope, you can try it with something smaller. And certainly if you've got a bigger telescope, go ahead and track all the things down that are listed even for the smaller apertures. And moving up to 8-inch and 12-inch and greater telescopes, we have 2 objects in the same field. The lovely large galaxy NGC 247. And in the article, I mentioned the needle's eye that's found in the galaxy, and that dark gap in the galaxy is visible in a 10 to 12-inch telescope, and that is on the northern end of the galaxy. Right here is kind of a dark spot within the halo, opposite end from where the star is. And then for much larger telescopes, we have this lovely little string of galaxies up here. This is the Burbage chain of physically connected chain of galaxies all interacting with each other. Quite a bit harder to see. You'll need a 12-inch or greater. I've seen the 2 on the ends here with a 12-inch scope. I've never seen this one right here, and this one only fleetingly. But an 8-inch scope for the larger galaxy, and then if you've got a decent aperture, go ahead and try to catch all 4 of these guys up here. They're like Pokemon. You got to get all 4 of them. And then our last, I believe, object in Cetus this month. And there are tons of great galaxies in Cetus. I haven't obviously talked about all these other ones that are labeled here on the chart. This chart's in the newsletter. So if you're looking for stuff that's interesting, every one of these ones that's listed here is going to be a nice bright target for your backyard telescope. But this last one, which is over here way low in the western end of the constellation, is a satellite galaxy to the Milky Way called WLM, Wolf, Lundmark, Melot, after the 3 discoverers. who I believe actually discovered it on a photographic plate. So they were not even visual discoverers for it. It's a very subtle glow against the background sky. You'll need a dark sky for this one, but a 10-inch telescope will show it. Kind of looks like the country of Liechtenstein here, that it's got that perfect shape. I don't know when and where I discovered that, but I can't get that out of my head now. And if you've got a large telescope, you can look for the galaxy's large, bright globular cluster just off the preceding or western side of it, right here as the more southern of these two starry objects. This is a star. This is a globular cluster in this galaxy, which is a satellite of the Milky Way, and is one of many faint, difficult satellites of the Milky Way. This one is obviously one of the better, one of the brighter ones outside of the Magellanic Clouds. Still very subtle to look for, quite large in the eyepiece. Use a wide field eyepiece to track this one down, and you may see it as a brighter part of the background glow in your eyepiece.
Quick question.
Yeah.
How come it looks like an elongated globular cluster versus a wispy galaxy?
This is a dwarf galaxy, so it's considered I believe it's considered an irregular galaxy. It kind of does have that look to it. It does also has a couple of star forming regions in it. I don't know that these have ever been seen visually. I'm sure they have. There's people out there way crazier than me that'll spend all night looking for that. But yeah, this is a lot like the Magellanic Clouds, only with even less star forming activity and even less structure to it. It's probably that this object has been through the Milky Way or has been disrupted by the Milky Way enough that it does not have any kind of large scale structure to it like you'd expect. Certainly not like a spiral or anything. It's just been tidally disrupted by the Milky Way.
Thank you.
And again, there are a whole lot of satellite galaxies to the Milky Way like this, but this is one of the brighter and more obvious examples of it. WLM, also known as UGCA 444. And I'm actually trying to track down this little galaxy that's not far from it, but I haven't gotten to it yet. But Cetus is crawling with galaxies. It has one open star cluster in it that's way out of the way from all the rest of the star clusters in the Milky Way. Has a couple of planetary nebulas. It actually even has a faint, very difficult globular cluster in it that wasn't discovered until about 20 years ago. So there's a lot to see there, but mostly galaxies and a lot of really good ones. So get your scopes out. That's what's up in the December sky, or at least a little portion of it. And maybe you'll see at the Oxbow. So bring the article with you, and I'll give out a prize to anybody you find some of these things. Not really, but consider yourself rewarded if you decide to sweep these up.
You know, you put up that last slide, and my first thought was that is a dead ringer for Liechtenstein. That was seriously my very first thought.
I think it looks like the California Nebula. It looks like a steak up there.
A steak?
The California, yeah. When I look at the California, just so it looks like a piece of tri-tip.
I think we should lobby to have it changed to the Tri-Tip Nebula. I really do. It's like that Deerlick group in Pegasus that name just makes me want to throw an eyepiece. It's like, how dare you? That would be like us calling something the Eagles Ridge Group. I mean, come on. So
All
now that
right.
I've displayed my violent tendencies for the group when it comes to throwing eyepieces and things like that. So, any questions, comments? Okay, I'm going to turn it over to Mel.
Well, I'm going to introduce Mel because
Okay.
hardly anybody knows who he is.
Thank you,
Okay.
Andy.
Yep.
Okay.
Thank you very much.
Okay, let me stop sharing here.
Mel Bartels' articles about telescope making and observations have appeared in Sky and Telescope, including the recent December 2022 issue. He's appeared as a guest speaker at astronomy conferences, and his telescope walkabouts are a highlight at the Oregon Star Party. He created the first popular computerized control of telescopes using stepper motors that was among the first open source software and hardware projects. He ran the first ATM listserv for 6 years, which served as a meeting place for amateurs. The IAU named asteroid 17823 Bartels in recognition for his contributions to amateur astronomy. Now retired, Mel began as a jazz and classical trumpet player, then segued into software development and ultimately management. More recently, Mel began working on thin, highly curved meniscus mirrors for very fast telescopes. But Mel is not just a telescope builder, he's an observer as well. He uses his short focus telescopes to observe very faint objects, and he records his observations by sketching them on paper. Plus, he's been a member of EAS for 50 years, more than 50 years. His presentation tonight, Faster and Fainter Drawings with 30-inch and 16-inch Telescopes and a Rarely Heard Perspective on How Telescopes Work, takes us on a journey to galaxies torn apart as seen through clouds of Milky Way galactic cirrus. Mel's drawings record observations long thought to be impossible, yet seen by William and Caroline Herschel 200 years ago. Mel will talk about his latest telescopes, both a 30-inch and 16-inch, and Mel will describe a new way to understand how telescopes work, an understanding not that dissimilar from the Herschels. So take it away, Mel.
All right. Well, thanks, Amy. And I trust all of you can see my screen sharing and hear my voice. And thanks, Andy, for the discussion of angular size. That's actually pretty important to my presentation. And I see we have quite a mix of people attending. Jerry Oltian, who's an editor at Sky and Telescope. Jeff Phillips, who has digital images published in Sky and Telescope, is one of the premier imagers on the planet. I see Howard Banich is here, whom I regard as the greatest sketcher living in the world. And probably some of you who are just starting out and hardly know much about telescopes. We're just at a star party here in Sisters. And the woman organizing the event brought out a scope and said, I don't think the scope works. Should I return it? And of course, she didn't have an eyepiece in it. And so we went in the box and we found a couple of eyepieces and she goes, oh, that's what they are. So, telescopes are not so easy always to begin wrestling with and figuring out what's going on. So in the right-hand side is one of my latest creations, a 30-inch. And you can see that I can reach the eyepiece with my feet on the ground. I don't need a ladder. I find that pretty convenient. And then on the left is a sketch I made of the Ring Nebula that I'll discuss a little bit later. So before I get going now, I want to talk about some of those who have died this last year. I think we should, or I'd like to remember them. The first on the left is Steve Swayze. He actually went to my high school, but he didn't get interested in astronomy until he ended up in the Bay Area, hanging out with some of John Dobson's group. And he's such a bold and creative telescope maker and mirror maker, culminating in the 40-inch that you see there. And he's on top of his 16-foot ladder. And there's some pretty wild tales to tell about that. He's from Portland. In the middle is Mark Cowan from Salem, who died suddenly recently. And he was such a clear explainer and understood optics and how to make them so well. It's such a loss that he's gone. At the time of his death, he was working on the Holy Grail telescope makers, which is an automated grinding machine that would polish the mirror, test the mirror, then adjust polishing to make it better. And then finally, on the right, John Wally, a Eugene Club member, and participated in the modern inception of the club in 1957. He was instructor at Lane Community College and taught many years worth of mirror making, mirror grinding classes. And he, besides being a strong club supporter, he made these incredible astro photos using eyepiece projection onto old-fashioned large format Polaroid cameras. One time he recorded a band on the planet Uranus, which at the time it was laughed off, but now we know actually does exist. It's just incredible. And so I like to think that every object has a story, every observation a tale, and every amateur a life worth listening to. In the over 50 years I've been a Eugene Club member, I've seen the club go through so many eras and so many groups of people that I tell you, every amateur who's ever participated in the club has had a story interesting to tell, and I sure encourage all of you to do so. And I suppose this presentation of me tonight is one of my stories. Not quite on the level of the Bigfoot story or the red UFO story, but we'll see. Oh, now how did we get to there? So let me see what is going on here. Oh, here we go. Okay, so here's some of my drawings of the Andromeda Galaxy. Of course, visually, at best, at least to me, it's just an indistinct smear in the dark skies. On the far left is a drawing I made of the galaxy with the 6 inches. This is actually a first light drawing. And you can see all that telemetry material around the galaxy. That's actually galactic cirrus, or what we call integrated flux nebula. Galactic cirrus is gas and dust thrown far out of the Milky Way by supernovae explosions, and it glows very faintly. In the middle is a drawing I made through my 25-inch scope, and it shows the galaxy much brighter and bigger. And you can see some of the detail in the galactic cirrus, although it's not quite as extensive, of course, because it doesn't have the field of view of the 6-inch. And so when I looked at the Andromeda through the 30-inch, I expected to see something like the 25, but maybe a little bit more. I mean, the aperture difference between the 30 and the 25 is not that great, but instead, the view through the 30-inch was much more detailed. The galactic cirrus broke apart into lots of detail. It was just a much better view than I suspected. Down there below it is my drawing at high power of Messier 110, which is the companion galaxy to M31. And if you see my mouse, it's this one right here. And these are some of the drawings that are featured in my December SkyTel 2022 article. So I go where the telescope takes me. I was not intending to get into galaxy observations again, because I'd had a 24-inch for so many years, and I'd just gone through so many galaxies and clusters of galaxies. I was really quite satisfied with galaxies. But the 30-inch, I aimed it in a general direction of the antenna galaxies, just, out of curiosity, and this is what we do for fun and enjoyment and satisfaction. And I came across this little galaxy down here. And when you first see something, you go, well, that's like the antenna galaxy, but what happened to the other galaxy? And so you entertain these wild fantasies. Did the other galaxy get zapped? And then you move the scope over a bit and you go, oh, here they are. Oh, wow, look at those antennae coming out of there. So to have this kind of detail in this field of view began leading me down the path of looking at galaxies. And so I came across NGC 4315, and it turns out that at higher power, I could see this tidal stream, some type of smaller galaxy that's being torn apart as it traverses through this galaxy and on around. And 4651, another galaxy that has these little streamers on the side. I was really gratified to see those. It was very pleasing. But over here, more galactic cirrus and integrated flux nebula. So I wasn't sure that I would see that with a 30-inch at all. A lot of these structures are really large scale and very broad and very diffuse. And at some point, the telescope will just look at such a tiny portion of it, you're not going to see much, or at least I thought. But then it turns out that the 30-inch actually shows a lot of detail. And now we come across a case of NGC 5907. So those two pictures on the right are done by professional astronomers at professional observatories, and ostensibly supposed to be of the same object. And if you take a look, you can see that these two graphics are lined up exactly, oriented and the same scale. But what has happened to this tidal distorted stream here? Why isn't it showing up over here? I didn't know that mystery until I went to look at it. Visually, through the 30-inch, I could see a little bit of faintness here, which corresponds to this part down here, and a little bit of faintness on the streak here, which corresponds to this over here. That's all very fine. But I also saw galactic cirrus, or IFN, up here, and I have yet to find a professional digital image that shows this IFN or galactic cirrus up here at all. So I'm really motivated to get back to this object and observe it some more to see if I can possibly see this second tidal stream. Is it real or not? Apparently there's quite a have it all out fight in the professional world over that. Here's a more conventional grouping of galaxies, R102, and it shows vertical streaking of the galactic cirrus and the tidal streams, the galaxies interacting and distorting each other. Here's Messier 96, pretty bright galaxy, but it turns out that there's a background galaxy that just happens to show through one of the arms, and that's this one right here. And so that's very gratifying to take a look at. So there's a Sixon catalog of faint galaxy groupings. This is 650, which is one of the more difficult groupings. This one here is actually star. There's 4 that I could see. I believe this is a unrelated anonymous galaxy here. This is the Owl Nebula in 97 and or galactic cirrus or IFN here. So really pleasing to see such disparate objects in the same wide angle field of view. Here are 2 groupings of galaxies. William and Caroline Herschel called them their favorite galactic double-double, kind of in a nod to Ellipse and Lyra, which is the famous double-double stars. And I believe this is called the Whale Galaxy, and this is called the Occupant Galaxy. But it turns out that I can also see galactic cirrus here between them. So that's really neat to look at and to think of the Herschels 230 years ago, coming across these for the first time and observing them and being astonished by how they look. And now on to the Ring Nebula. So it turns out in very big scopes in dark skies, you can see that there's an outer shell to the ring. And in the 30-inch, as opposed to the view in the 25, I can see a little bit of structure coming through here. This galaxy over here normally is really difficult for me to see. I just really struggle with seeing it. But a few times, my eye and my brain and the sky conspired to where this popped into view really dramatically. But what astonished me through the 30-inch is this galactic cirrus here. And all the decades and countless times I've looked at the ring and I've not noticed this before, and it's just right next to the ring. One of the faintest globular clusters is Palomar 5. This is my drawing of it. You can see there's a faint unresolved glow behind this glitter of small stars. It just is a pretty high power. So just knowing something about these objects makes them much more appreciated at the eyepiece. This is really distant globular. This one doesn't need much knowledge behind it at all. It just looks spectacular through the eyepiece, because the glittering stars of the globular cluster are so bright and so resolved. And then there's this big glow to the cluster, and this frighteningly bright galactic cirrus right here. And all the times I've looked at Messier 5 and I've not noticed this until recently. You know, what's going on? How to explain that? Am I just so naive and close-minded? I can't see what's literally in front of my nose or my eye. And it turns out that between the Andromeda Galaxy and the whirlpool down here, or not the whirlpool, forget the nomenclature for M33, there's a stream of galactic cirrus that flows between them. And I got pretty good at traversing this, just following it along in a telescope and leading me from one galaxy to the other. It's about 10 degrees between them or so. Also, it turns out there's some very large scale structures. This is this constellation Sagitta right here, which, you know, is not the biggest constellation in the sky for sure, but it does have some size to it. And M71 is this glittering grouping of tight little stars in here. It's very pretty, but there's this huge bubble around it too. That's quite striking to see. And then the California Nebula, which in smaller scopes has always just been kind of a long smear at best. It's pretty faint, but in the 30-inch, it's broken apart into these streams and details. Wasn't not expecting that. That's really wonderful to see. And so, switching gears a bit, this is Messier 16 and the Pillars of Creation. This is through a night vision device. Ed Allen from Montana met up with Howard Banage, and Barbara and I drove out to take a look. And wow, it's hard to describe. This is actually a NASA photograph that I manipulated to look as best as I could to match the view through the night vision eyepiece. The view was very visual, eyepiece oriented. And these areas here around the pillars were glowing really bright. It was just an astonishing view. And as it turns out, it's a combination of the speed of the 30-inch at f2.7 and the home silvered primary that is highly reflective in the longer wavelengths that the night vision device is most sensitive to. And then that the night vision device had a filter on it, which helped the contrast. But yeah, this is really kind of almost life-altering view. But of course, we looked at a number of objects that night, and one of them that struck me the most is the Pelican Nebula, which is in Cygnus next to North American Nebula. And I just finished a drawing of the Pelicans with the 30-inch, which I thought was pretty representative of the view. And I was really proud that I am able to see these little black streaks here, the tips of which are star-forming regions. But then when we put the night vision device on, we could see the outflow from these stars, and we could see the outline here. And it was just, and all these dark nodules and so forth in here, it was just astonishing view. Okay, so we're going to gradually transition over to how a telescope works. But the telescope I've just finished is this little 16-inch here. It's a 7-pound mirror, 25-pound tube assembly. And I kind of built it as a relaxing, fun project after the 30-inch project. It was a lot of joy to make the mirror and put the scope together. It wasn't near as demanding as the 30-inch. I was able to do it a lot quicker. And the first object that I sketched with it is the larger Pleiades. So Hermann Goldschmidt first, as far as we know, discovered the nebulosity around the Pleiades with the 4-inch, and Walter Scott Houston made a kind of a cryptic note in Sky and Telescope circa 1940 that it was known that the Pleiades surrounded by a bubble of nebulosity, but I didn't know that when I saw it on first light with my 6-inch and kind of rediscovered the Pleiades bubble. And so in a 16-inch, the bubble actually kind of breaks up into blotches and nebulosity. And we know that the Pleiades as a star cluster that's gradually coming apart is just happening to be traversing through this nebulosity and is illuminating this gas and dust. But some of this out here is legitimate galactic cirrus too. And I suspect that there's actually an outer bubble surrounding the Pleiades bubble, which surrounds the Pleiades itself. And if you take these three stars here and you look at them through the 25-inch, the nebulosity shows a lot of interesting detail through here in the scope. So I hope to take a look at this other part of the Pleiades and see if this loop continues or what nebulosity might be out there. So the description of how a telescope works as typically understood by amateurs, I don't find that satisfying. It doesn't seem to predict what I see in the scope. And I'm kind of interested in knowing the why so that I can tune the telescopes that I design and build to better ferret out what I'm looking for. So this next part then is going to be about how a telescope works. It also turns out that professional opticians, while they do the ray tracing that we see as amateurs, they also talk about telescopes and optical performance in very different terms, very strange words and phrases like four-dimensional phase space and so on. And while I've gone through and watched the lectures on that, and the math is actually rather awesome and not difficult, it's something I never really heard of before. But other than just to let you know that that exists, we're not going to go into that mathematical depth because there's a simpler way to do it. So before we do that, let me stop for two reasons. The first is, does anyone have any questions or comments about my drawings or anything that I've said so far?
They're super amazing.
So Mel, do you draw in pencil on white paper, or do you draw with like white chalk on black paper?
Both. I used to do white chalk, I'm sorry, on black paper at the eyepiece. And, under the dim red light of a flashlight, I thought I was the greatest artist in the world who's ever lived because it looked great. And then I brought it in and looked under the cold, harsh light of the next morning, and it was the ugliest, most kindergarten-ish stuff I'd ever done. So I thought, oh, I better come up with a system where I can like fix this in daylight. So I've gradually switched over to charcoal and white paper where I can adjust it. And then actually what I do is I work on the drawing for the first night. I'll often take ink on paper and just scratch out a bunch of notes and try to give an illustration along with my visual memory. I'll then compose a more formal picture the next morning, but that always has questions and holes and, is it to the left of that star or to the right of that star? My ink scratches are like not too indicative. So I invariably go back for the second night and finish it off. And I'll say a sketch takes me on average 2 hours per each of those 2 nights to do. So I do both, but mainly charcoal on white anymore, composed from my ink scratchings at the night. Any other questions?
I'll echo the question that appeared in the chat. Is an integrated flux nebula a gas sort of a trail between galaxies? Can it be used to identify interacting galaxies, or how do cosmologists refer to them? Is that a cosmological term?
It's an astronomical term, and the answer is no. It is not between galaxies. It is within our Milky Way, and we tend to see it. But here's the thing: we tend to see it away from the Milky Way itself. And the reason for that is that this is gas and dust that's been blowing above and below the galactic plane. So when we look away from the plane, like toward the little cluster of galaxies, for example, there's going to be a lot of this dust and gas that we can see. And William and Caroline Herschel began to suspect that there was something there over 200 years ago. And he wrote just before he died that he had become convinced that what he called the floor of the sky, or what we call the sky background, varies almost everywhere he looked, particularly away from the Milky Way. It varied. Well, that, along with his catalog of 52 very faint nebulous regions, well, as far as I could tell, it was suppressed because people couldn't build telescopes as well as he could, and they just couldn't see that. And secondly, they were not skilled as he was and as an observer. And so it's taken centuries to come across this. But this is actually a really, really big deal and problem and challenge for professional astronomers because they have to subtract that gas and dust that's intervening between us and these distant galaxies. And you might remember the, what was it, the BICEP study at the Antarctic didn't calibrate this dust quite right, and they had to retract their findings. Having said all that, it turns out that there is gas and dust between galaxies, and we call that the circumgalactic dust, but that's not anything that I've been able to see yet. That's a whole series of magnitudes fainter. So it's really interesting.
Really
you know, when I was a kid, it was like, go and look at this pristine clockwork solar system and these wonderful galaxies. And now it's like, oh, we can just not tear away enough dust to get out of the view so we can look at these things. It's everywhere.
That's fascinating. Thank you.
Okay, so the next section, I know some of you are really advanced and others are just starting. And it's a bit of a challenge for me to explain this because I want to go deep enough to where it makes some real sense, but I don't want to go down the rabbit hole so much that we get lost either. So I'll try to pause and ask how we're doing and what questions you might have as we go along the way. So first of all, at least for me, it really helps if I stay grounded in what the heck I'm trying to think about. So what is a telescope? What does it do? Well, first of all, it magnifies. This is an example of what Mars looked like. And this is the first night I had my first scope as a elementary school kid. Mars was out there and it was kind of orange, and I aimed my scope at it. And it was still orange because I didn't know anything about that. You're going to really only see detail on Mars when it's at opposition. So I did learn that, but even so, 50 years ago, this is my drawing of Mars through an 8-inch scope. And this is before the digital camera age. So, but still, I think this is a pretty good drawing of Mars. So that's the first thing that a telescope does, is it magnifies Mars from this to this. It also resolves, it adds detail. This is a drawing of Jupiter from an earlier era in my life with a 14-inch scope. And then finally, it brightens. And here's my composite drawing of the Veil Nebula with the 25-inch. And this is a series of drawings that I've mosaicked together on the computer. And the Veil Nebula is something that you cannot see with the unaided eye. At least I've not seen it or nor heard of anyone who's done it. And yet through the scope, you see this marvelous detail. So how can that be? How does the telescope really brighten this image? And as an example, here's M87. Now I know that a few eagle-eyed observers have managed to see M87 with the unaided eye. I'm not sure I can say that I have. And this is my sketch of it through the 25-inch at low power, showing, again, galactic cirrus. And these little two companion galaxies, this is kind of in the heart of the Virgo cluster. I think M87 is a member of that. But at high power, we see these two companion galaxies, and then we see two background galaxies. This is not the black hole jet, although I suspect some amateurs, when they first see this, they go, that's it. Actually, the black hole jet is something much more difficult right next to the nucleus. It's very small and relatively extremely difficult to see. Even so, there is still some galactic cirrus that comes in here. So this is an example of what a telescope does for us. So can you make a telescope without a lens or a mirror and without an eyepiece? What do you think? And I'm curious to hear your thoughts on this. I asked the OpenAI chatbot, which is an impressive piece of software, and it claims that you must have a lens or mirror and an eyepiece, or it's not a telescope. But what do you think?
I think if you had a very strong magnetic field, you might be able to pull it off without a lens.
Yes, well, see, that's Jerry, the science fiction writer, talking there.
Sorry, it just came out.
So any other ideas or thoughts?
I think
Okay.
given the fact that the Open GPT chatbot has been 100% right with every single question that's been thrown at it, that has to be true.
What about the Mercury? Well, I guess that's still functioning as a mirror, but the Mercury mirror up in Canada that uses a pool of mercury instead of a lens or anything like that.
Right, and did you hear that they are finishing up a 4-meter liquid mirror in, I think, North India?
I did not know that. But I think they use a camera as well instead of an eyepiece. So
Yes, yeah.
yeah.
How about a galaxy, you know, a lensing galaxy?
Oh, I like that. I hadn't thought of that. That is excellent.
That can serve as a,
Although you could kind of say that all the dark matter in that foreground galaxy cluster is acting as a lens.
right, it is called lensing. So I guess that's kind of cheating, but gravity lens.
Well, so here's the thing. Astronomy is like really hard. So I don't think there's like, there's no rule against cheating in astronomy. You do what you can to make these things visible. Okay.
So, hello?
Yeah, go ahead, Alan.
All right. I was going to throw out there that I don't think radio telescopes have lenses or mirrors.
They do. That curved parabolic metal,
Okay.
that works because radio wavelengths are very long. And as far as the radio energy coming in, that looks like a solid surface to the radio waves. And we're going to talk about that in a little bit. So I would say that that is a mirror.
On the other hand, you can just use a dipole antenna and do observations of like Jupiter or the center of the galaxy. So those aren't mirrors.
Yes, that's excellent. I hadn't thought of that. Well, how about a pinhole solar projector? Is that a telescope?
Yes, it is.
And so I found this picture off of time.com or life.com of a bunch of kids with their school-made solar projectors in 1963. And since the news is about JFK's death, being a little kid when he was assassinated, I do remember that the Earth changed that day. But I would say this is a telescope. And so I'm going to piggyback now a little bit off of what Andy was talking about. Because the pinhole projector, you have this little pinhole in the center and a sun way out here. And we can't, well, actually we do know what the size of the sun is, but when we look in the sky, it's just easier that we talk about these objects in angular size. Well, you know, the sun is 93 million miles away and it's so big. It's just simpler for us to say, well, it's the size of a half a degree. And when light goes through this pinhole, how does this half degree get turned into an image size way down here? I mean, how does that work? You know, it's always kind of been a bit of a mystery to me. Well, it turns out that at 115 inches away from the pinhole, the sun's image is an inch wide. And at the halfway point, it's a ½ inch wide. And so you go, oh, angular size and image size down here are interchangeable. And I've always remembered this rule because my first stereoscope was an 8-inch f7, 56-inch focal length, that at every 57.3 inches of focal length, the image, a 1 degree image is 1 inch. So you have 1 degree at 1 inch at 57-inch focal length. So angular size and image size are interchangeable. That's what I want you to see here. Now I'm going to ask you 2 more questions which have a bearing. I think they do, but they might seem a little out there. So the first one is, can you start a fire with a magnifying lens and moonlight? And this quickly devolves into a support or ancillary question. What temperature is the light coming from the moon? I mean, the sun is almost 10,000 degrees and the moon reflects that sunlight. So isn't the light from the moon like at 10,000 degrees or not? So what do you think? Can you start a fire with moonlight? And just imagine the biggest magnifying, most highly curved lens that you can think of. What do you think?
Would it depend on how close to the moon you were?
So let's say that you can get as close to the moon as you would like. Because it turns out it doesn't matter.
Oh.
So I'll give you that one, Amy. Okay. Now I voted no on that one, and it's kind of in an intuitive sense. And later on, I'll tell you what the answers from at least a physics viewpoint is. But I can tell you also that if you want to go on the internet and you want to just drown in never-ending argument, go on to discussion forums like Physics Stack Exchange, where this is being discussed for years and years with countless people. It's pretty amazing.
Wouldn't it still be the same Kelvin temperature?
What would be the same?
Wouldn't the reflected moonlight light still be the same Kelvin temperature as the sunlight?
Well, why would you say that?
Because it's the same light. It's the light coming from the sun bouncing off the moon.
Yes. If that were the case, then wouldn't the moon be 10,000 degrees warmth then?
Good question, but it's the same light. It's like, it's got to be, to me, I think it would have to be the same Kelvin temperature.
Right. And that is a really tricky one. That is for sure. So it brings up a really interesting question, which I'll just put in the middle here. When a photon or a little bit of light comes in and hits the mirror and bounces off, is it the same photon?
I would
I
think
don't
so.
think it is.
It is not. It has been absorbed and a new one has been emitted in the exact appropriate incident angle, which I find absolutely amazing.
So it's a reflection then, huh?
Yes, and the same with the lens. That photon or a little bit of wave, light wave energy comes in, hits the lens, a new photon's emitted, it's then travels through a bunch of photons are absorbed, emitted, comes out the other end, different
So,
photon.
Mel, doesn't that mean that there's necessarily going to be a Stokes shift? I mean, is there a shift in the, you have to lose energy somewhere, so there's going to be a shift to a longer wavelength.
It turns out that the spectrum of the moon and the spectrum of the sun are remarkably similar.
But is there a spectrum of the moon just a little bit redshifted? It would have to be if that's true.
Not enough to justify the answer to your question being yes.
Okay.
Okay, so let's move on to the second one. Otherwise, we're going to get bogged down.
Yeah.
So I didn't think you could do moonlight. Now, why do I do that? Hold on. Here we go. Sorry about that. I guess I hit the end key. Okay, so we're back here now. So, intuitively, I would say you can't start a fire with a magnifying lens. Now, what physics says and what you think, or I think intuitively, are not always in agreement. And there's a wonderful explanation on this on XKCD, the comic strip, that he actually goes into perfect depth using solid physics to explain this. The second one, though, can sunlight be focused with a very strong lens? And you can imagine any lens you want, into a spot hotter than the sun's surface. So the sun's surface is almost 10,000 Fahrenheit. Can you possibly focus the sun and get whatever it is that you focus the sunlight onto to be hotter than 10,000 degrees? And by the way, if you do this for real, if you do concentrate a lot of light, do protect your eyes, because the specular reflection coming from that hot spot can actually hurt your eyes. So intuitively, I would say you can focus sunlight. I mean, you get this lens and you're focusing all the sunlight and the sun's really hot. Can't you get that hotter than the 10,000 degrees? So what do you think? Is that your intuition, or are you going to be cold-hearted physicist and say, no, that can't be true? Because otherwise, why would I be putting it into a presentation, you know?
You're talking about the Archimedes death ray, right? And Archimedes was hypothesized to have made a reflecting lens to burn ships at sea from the shore.
Yes, well, yes.
Which could be done.
Could be done.
The thing that makes me doubt that you can make it any hotter than the sun's surface is that the image created by that mirror or lens is going to have some dimension. It won't focus down to a spot. Because
Jerry, you gave it away.
oh, I'm sorry.
Oh, that's perfect, because that turns out to be something that is one of the great explanations. And so the answer is, even though intuitively I think you cannot get that sunlight focused into the perfect dot. You just can't do it. It can be a spot, but it can't be an infinitely small dot, and you will never get that to be quite as hot as this, or hotter than the sun. You can get it to be almost the sun, and then the real question is, why can you not get it to a dot, or to a perfect, infinitely tiny dot?
I'm guessing it has to do with the airy disk, the smallest resolution that the mirror or the lens is capable of. But that would be backwards, in that the smaller the mirror, the larger the airy disk. So if you had an infinitely large mirror, you could get it down to an infinitely tiny dot. So that doesn't make sense.
It doesn't. And see, this is why I'm looking for better answers.
Okay.
So let's go on, because I think I have an answer that will satisfy you. At least it satisfies me. So the third question to ask is something that I came across, and I found it magical or mysterious. And that the input angle times the input area always equals the output angle times the output area. So this is a little hard for me to accept. So I took a CAD program and I drew it out. So here's my drawing of the Andromeda Galaxy, typically given as 2.5 or 3 degrees wide, but I showed that the galaxy is actually 5 degrees wide in my article in Sky and Tell. So here we have a 5 degree wide beam, and I drew my computer drawn 5-inch lens here. Okay, and we take the size of the object on the sky, thanks to Andy's explanation. We know what 5 degrees is, 5 squared because it's an area. And we take this lens, which is 5 inches, and we square it, and just because we want to, and we get to 625. Now, let's presume that this lens is an f3. And we know from the earlier example of that solar pinhole projector that therefore at 15-inch focal length, this image 5 degrees is 1.3 inches wide. Okay, we figured that out. And now we use our handy dandy CAD program and we ask it to tell us what this angle is here. And then we square the angle, we square the area, and we get 620. So they're the same numbers. Is that like weird, or is that just coincidence, or just so? I mean, what's going on there? And why do we not advance now on the screen? Here we go. So étendue is a French word, and it just means optical throughput, or the spreading out of light. And I want to give an example because apparently I'm often criticized on forums for invoking some type of mystical Macbeth witch type think, well, it's because of Entendu and New Age aquariumism, that Mel says you can see this stuff. And I'm not saying that. This is cold-hearted dagger type math. So here's IFN that at CoCam, it's this beautiful structure through the 10-inch, and I dimmed it down to what it looks like when I mask the telescope down to 8 inches. You can still see it, but it's fainter. So more aperture, more light throughput. That makes sense, right? Bigger hole, more light rays are going through there, right? The other way is increasing the field. This is 100-degree eyepiece, 80-degree eyepiece. This is on the Whirlpool with the 25-inch, I think. And you can see that the 100-degree eyepiece, because of the larger angle, and let me just go back here. This larger angle here is what I mean. There's more light coming in because the area has increased. And so that's why we actually multiplied the two together. And if you're a professional optician and you know 4D phase space math, you go, well, of course, this is what you do. But as an amateur looking at this, it feels a little arbitrary. But what we're really getting at is light throughput. It's the size of the mirror or the lens and the amount of angles. So if you double the angle, you get 4 times the light. Now here's the weird thing. You take the scope aperture and the true field in the sky, and you compare it to what's happening at the output of the telescope, which is the exit pupil or eye pupil, times the apparent field, and you get the same number. So that to me is astonishing. And it's the same number, same distance here. So why is that? So now I get to talk about Emmy Noether, who's arguably the greatest abstract mathematician to have ever lived, about 100 years ago. And Einstein brought her in to help explain facets of general relativity, particularly is energy conserved. It wasn't clear from Einstein's equations at the time that it was, and she showed that it was complicated, but it could be, or that it is conserved. But she also came up with the Emmy Noether law that says that for every symmetry, there's a conservation law. For instance, the conservation of energy comes about because the universe is the same a second from now as it is now. The universe doesn't change. That's conservation energy. Conservation of inertial momentum comes about because as the ball in space moves a foot to the right, space is the same. X, Y, Z to the right is where you're at now. And so while the conservation law of Entendu is not one of these fundamental laws in that it derives from other laws, it is an Emmy Noether equivalent type law. It actually comes from the second law of thermodynamics. So what I'm saying then is that these two numbers agree here is not coincidence or just happenstance. It's because of a fundamental aspect of nature. And I'll talk about this, and this is what I'll try to explain. Second law of thermodynamics. I know it's not very sexy to say that, but it comes from this formal conclusion that physicists and opticians have come to, which entropy can never decrease in a passive optical system. And so the example of this, I would say, is an art museum, because I find this to be pretty abstract and hard to think through. So art museum, you let in 1,000 people, and they're all clustered at the front door when they first come in. Now they spread out across the different paintings and so forth. And you think about all the different ways that by randomness, the people can arrange themselves. What are the odds that they will ever come back and coalesce all 1,000 of themselves onto one painting? It's possible, but the odds are infinitesimally small because there's so many other possibilities. They're spread out evenly, they're clustered around a few of these paintings in this wing here. The odds that all of them get clustered back together is just essentially 0. That to me is the second law of thermodynamics. Consequently, we can never truly focus light into an infinitely tiny point because of this. And I'll explain more reasons why that is. Now, Jerry already alluded to that there's another complication, that light has wave nature to it, and it forms the area disk, and that gets in the way of an infinitely tiny point. But let's say that the light was infinitely tiny wavelength. But there's another way to look at it too, and that's the back and forth violation. So the fundamental reason that a physicist would explain that you cannot focus sunlight to get it to be hotter than the sun is that whatever can go through the lens or telescope can also go back through the scope. A telescope is agnostic. It has to work both ways. And so if you took that 10,000 degree sun and you focused it to 12,000 degrees, that 12,000 degrees could flow back through the lens to the sun. And then it would heat the sun to 10,000. And then the sun 10 or 12,000. The sun 12,000 would come back through, hit this point and get heated up to 14,000, go back to the sun. Then the 14,000 would come back through, get heated to 16,000, and you'd have this runaway violation, which clearly doesn't work. So that's really why we can't do this. It's just an aspect of what we observe in nature through the second law of thermodynamics. Another way that I think is really interesting, and this gets to where something that I guess I didn't understand, because for a long time I thought about ways to take multiple mirrors or lenses and try to get them all into my one eye at once. And every time I did it, and I would actually start to draw it out, I couldn't quite make it work. And now I understand why. And it's because if all of these cones of Ecton somehow overlay each other, and the light wave makes it through and comes down to this little point, well, remember that a telescope has to work backwards too. This light ray going back through, which Ecton cone should have followed back into? It doesn't know which one it came from. So that's the back and forth violation, I call it. And that's another reason why it can't work. Consequently, as the cone of light is made steeper, the area of the beam must be smaller. And this is what Jerry was alluding to here. We can bring this in even closer, but this 1.3 inch that represents the 5 degrees would be half that size at half the length, quarter the size at quarter the length. So every time we increase the angle because of the law of conservation and to do, then the area has to be smaller too. And that seems intuitive to us when we work with telescopes and lenses. But that is a consequence, or that is the conservation law of and to do. Now, here's where I'm going to all this trouble to explain all this and where I hope the payoff is. The consequence then is that the lens and mirror only makes light sources appear to take up more area of the sky. They don't make any single spot on that object brighter. Consequently, the surface brightness of the object can never be increased, only nearly matched. Now, I used to explain this all the time of, well, you know, the lens increases the light by 100 times, but then you have to magnify it and by 10 times, and then, well, there you go, it evens out. But it isn't a just so thing. It's actually a fundamental consequence of the laws of the universe that we see, that the surface brightness of the object can never be increased. The lens and mirror can only make that object appear to take up more area of the sky. They don't make the object actually appear brighter. That, I think, is a stunning thing to say, because then how do we manage to see these objects? So I'm going to pause there and see if you have any questions or comments. Okay, it must be a stunning presentation. We will continue on.
Mel, it really is. It really is a stunning presentation. I just wonder if you went to a lot of trouble to say I mean, I think one of the more there's certainly, this has to play into it. You have to have a shift in the wavelength of light to a longer. Whenever reflection happens, you lose energy. That would be the Cliff Notes version of this. And then the other is, yeah, you can only put field stops on an object. You can never, you know, all you do is constrain the field of view, right? You can never squeeze more light out of it. But I just was.
Yes, that's correct.
that's really the way I would. That's how I've always seen it in my really simplistic view.
Right.
Is
So I'm going to all this trouble to convince you that it's a fundamental law of the universe as to why an object cannot appear brighter to us. It's not just a just so type thing. It's actually
Yeah.
because of the universe. So that's why I went to all that trouble to explain it to you.
no, I love this. Thank you. This
Okay,
is great.
So now we're going to go back to how I learned how telescopes work and how it's illustrated, however badly, from time to time. And so I want to just go through this really quickly. We have an object at infinity or nearly infinity. We call this the entrance pupil, which is the diameter of the lens or the mirror. It forms a real image here at the focal point. The size we now understand from the pinhole projector, how that comes about. And you could put a piece of paper here and see the image and sharpness here. You could put a camera here, take the lens off because you already have a lens here, and it will take a beautiful digital image of what we call it prime focus. Now look at this eyepiece here. It starts with this real image, and it ends up in this exit pupil here, which is not an image of the object. We call it the Ramsden disk where all the light goes through. And all sorts of really interesting things go on here. First of all, this exit and this entrance, remember telescopes can work either way. This can become an entrance and this can become an exit. And we know from the law of conservation and do that this angle here and this angle here and their areas all have to work out to be the same number. So that explains why the exit pupil is whatever size it is. This angle here is actually the magnified, apparent magnified image of this object arrow here. It looks like it's this big. And then what the eye does as a wonderful instrument is it focuses it on our retina. The distance here is the eye relief. We put our eye lens here. And we have the eyepiece focal length and the objective focal length. Okay. Now, you see these symbolic pictures, but I wanted to draw it out for real because, you know, things are like more extreme than this. And so here's the 13-inch zip dog. And you can see that the entrance is this 13.2 diameter mirror. It comes down to, you can't even hardly see it, this little 1/5 of an inch exit pupil. And the ratio of the two is the magnification. And since the eyepiece is a 100-degree eyepiece, you now take 100 degrees by 70 power and you get 1.4 degree. I'll explain how you get to the magnitude here in just a moment. Herschel, he decided that the best way to rate telescopes was to set them at a uniform 5mm exit pupil and rate the ratio of the entrance pupil to the exit pupil. He didn't know about et-tu-do or anything like that, but he knew from experience with working with these scopes that somehow that was a relevant number. He called it the space penetrating power. So at 67 times, probably should be 70, just rounding errors. Resolution at this magnification, which is 3.5 arc seconds, but we know a 13-inch mirror can resolve more than that. So I'll talk about that in just a moment. And so this is what really happens in a real scope. This is really tiny, and this mirror is relatively really big. And that also tells me that any scope that you use is so overwhelming in size to the output of the exit pupil that, you know, in one sense of the word, well, should I get a 6-inch or 8-inch or 10-inch? Just get a scope. They're all so overwhelmingly superior from this viewpoint. Okay, so then what does the eyepiece do? Well, I alluded to it a little bit earlier. It produces a collimated bundle of exit light rays, which we call a cone of et-tu-do. It can be calculated in this 40 phase space, but we don't need to do that formal math. We just take the area times the angle. It redirects the light through the to the exit pupil into our eye so that our eye can focus it to the sharp image on the retina. It's subject to law of conservation, just like the lens. And as such, it also has a focal ratio. Did you ever stop to consider that? And it's like, whoa, kind of stops you in your tracks. And you go, so because of conservation and to do, because light can come in the other way, well, the eyepiece needs a focal ratio too. So what is it? Well, it's just the eyepiece focal length divided by the exit pupil. But the exit pupil changes depending on the primary mirror. So in example, I just showed you in that 13-inch f3 mirror, 17mm eyepiece and a coma corrector, an exit pupil of 5mm, and you put it all together and you find out your eyepiece focal ratio is f3. And that's the same as the mirror. So is that a coincidence that the two work out? The answer is that it's a consequence of the conservation of event and do. The light coming in has to resemble the light going out. So now we get to talk about, well, then it's sending it into the eye, which acts as its own optical device. So does the eye have a focal ratio too? And in your dark adapted dark sky eye, yes, you do. Your eye is about f2.1. So the eye has a focal ratio. Should it be the same as the telescope, or does it matter? So the answer to that kind of shows our understanding of everything that I've said. So what do you think? Are we throwing light away when the eye is f2 capable, but the scope is only giving you f3, or does it matter? So that is a question for you to venture a bold guess.
Well, the common wisdom is you want an f2 or you want a 2mm exit pupil. That's it. So yeah, it doesn't say anything about focal ratio.
Yeah.
So yeah, I don't know. I haven't got a guess.
Well, the answer is that the eye is an independent optical system. The telescope basically produces an image of the output. That's all it does, is just shrinks it way down, increases the angle, and in effect gives you that little magnified tiny little spot that you're going to inspect with your eye and spread it across your retina. So that the eye has an f2 and the telescope is something else doesn't matter, because they're two separate systems. What does count is how we fill up the eye with the light. And by the way, now that we know the eyepiece is f3 and we know that f3 is really difficult, it helps explain why these eyepieces cost more than many telescopes do and why they're so hefty in size. So before we get there, there are actually 4 magnifications. First of all, you can look at the size, as Andy described, of the object in the size or in the sky, and then you look at the size as it appears in the eyepiece, and that ratio is a magnification. We used to do that in the old days when we would time stars going across an eyepiece, and we would deduce the eyepiece's apparent field of view from that. The second way, the second of the 4 magnifications, is you simply take the primary mirror focal length and divide by the eyepiece focal length. The next way is that you can take the entrance pupil and divide by the exit pupil. Should be the same number. And because of law and to do, we also know that the converging angle of the entrance cone of light divided by the diverging angle of the exit cone of light is also that same magnification. So there's actually 4 ways to get at magnification here. Okay, so on to point sources. So Leonardo da Vinci, did he invent the telescope 100 years before, Galileo got his hands on it? So he was describing, if I recall right, a type of telescope that was inspired by the mathematical rage of his era, which were these catacostic curves. And a catacostic curve could actually fit a parabola in certain cases. But what he didn't know was that light had a wavelength. And so he thought that the telescope, he was thousands of times off over how precise a telescope needed to be made. Just didn't know the wavelength of light. Well, as it turns out, this wavelength of light doesn't do us absolute favor either, because stars are so far away that for us to resolve them, we would either need a lens or telescope that's like a mile in diameter, or light would have to be thousands of times shorter wavelength. So the long wavelength of light compared to the resolution needed does some funny things. So you might remember in physics, one of the most astonishing experiments that you can do is the double slit experiment, where you get these bands. And it's commonly done where you cover up one of the slits and then the banding pattern disappears. Actually, the banding pattern from that one slit is there. It's just really broad because that one slit just doesn't have the resolution of the two slits side by side. And so that one slit has a banding pattern, and our round lens or mirror also has the same type of pattern too, except of course, because it's round, it'll be in circles. Here's the F3 mirrors example, and we see that the area disk of visible light is, let's see, 10 hundredths thousandths, 1.5 10,000ths of an inch in size. And it turns out that it doesn't matter how big of mirror you have here, all the light knows that it's coming in at this angle, and it produces an area disk of this size. This could be my 6-inch f2.8, or this could be the 200-inch Palomar scope at f3.3. Light doesn't know. It produces an area disk of about this size. Of course, the angular resolution of the 200-inch is incredibly much more than a 6-inch, so you resolve more. But the actual area disk that you measured, get in there with a tiny little ruler or something, same size. Now look what happens when we go to an f6 mirror size. The light spread out much less, the area disk is larger. Doesn't matter what size of mirror, all we know is that the area disk is twice as large. So shorter wavelength of light, smaller area disk, light only knows the cone. But a larger mirror is finer angular scale, it's more resolution. So N2 still applies, but the long wavelength of light compared to the resolution needed results in this area disk, which is thousands of times bigger than what that star image would otherwise be. Okay. So any questions about point sources then before I go on? Okay, we'll go on. So then I just made this case that you can't make an object like brighter, you could just make it bigger. So stars though, because their unresolved light always ends up in the same size area disk, the stars get brighter as the mirror or lens gets bigger because the area disk stays constant. So you're pumping in more light into that disk. But how about extended optics? So this is where I think the magic happens. So the eye brain becomes aware of a very faint object when the object is about 2 to 3 degrees in apparent size. The faintest viewable of the galactic cirrus I showed you is about 25.5 magnitude per square arc second. The night sky at best is 21.8, 21.9, maybe 22 magnitude. So we're talking a contrast of just 2%. I looked it up. There's 91 million rods in the eye. It would take 25,000 adjacent rods for a 2 to 3 degree apparent size. At 2%, we only need 500 of those rods firing compared to their neighbors for the processing that goes on behind the eye that then switches to the further processing at the back of the brain. Only takes 500 extra of these rods for us to become aware of it. I've looked it up. Apparently a rod can respond down to 1 photon, but typically it takes 5 to 10 photons for that rod. So we'll call it 5,000 photons that the eye can detect if the object is spread out enough. And if you look at CCD specs, you'll see that's not that dissimilar to what a digital camera does. The eye is amazingly competitive. Now, it can't quite do the detail of the digital camera. And of course, it's subjective, it's conscious, but it's amazingly competitive. And now we can begin to understand how we can become aware of these and why deep sky filters are so effective because it helps our eye. Far more rods are firing off compared to the neighbors now. This contrast goes way up, and we can consciously perceive the object. So that to me is the real explanation and the real understanding of why these really faint structures are viewable under certain conditions. So any questions about the eye?
I have a question about the eyepiece.
Mhm.
So apparent field of view, the larger, the more light comes through, you said? Correct?
Yes, the larger the N2 number, that's correct.
So if you have a larger apparent field of view, you're gonna, well, obviously you see a wider field of view, but you're seeing more light coming through also.
Right, spread across the entire field.
So when I was totally blown away, I think it was 2016 Oregon Star Party, and you showed me the first time I'd ever seen, I think it was 100-degree field of view you had on your 13-inch.
Yes.
Is that correct? That
Yes.
totally blew me away. And so I invested in all 100-degree field of view eyepieces.
How's
And
your pocketbook doing?
you know, I saved for it and it's all done now. So but I'm happy with it. They're heavy and they're clunky, but they're cool too, you know?
Yeah. So I want to be clear. This whirlpool galaxy here and this whirlpool galaxy here are the same spread out brightness. Going to 100 degrees didn't do anything for that. What it did do was give me a brighter field, bring in more light, so I could see more contrast out here and see these structures over here. Maybe you notice it coming out here in this band down here, but when you get this bigger field of view, they're easier to see. So I call that discovery mode. When you're looking for these for the first time and no one has seen them before and there's no digital image of it, you know, you just need this to be aware of it. Once you become aware of it, you can use a 80 or 60-degree eyepiece and you'll see it. You'll have to move the scope around more, but that's where it comes in.
The other thing about those eyepieces is if you have a smaller, like an 80 or a 60, you see everything just by putting your eye there. But with 100, you kind of have to move your eye around to look at all the different angles or the edges to see it all.
Right. Okay, so that brings up an interesting point. How are we doing on time? Okay. It's getting to be a little long. Right. So I think it's a mistake to try to hold your eye still. I think you're better off moving your eye around.
Yeah.
And there's for several reasons for that. But ultimately, I like moving my eye around. It's easier to do that in a wide angle eyepiece. And then when I do move the scope to increase the field that I'm looking at, I don't have to move the scope quite as much. Whereas if I have a smaller angle eyepiece, I have to move the scope around a lot more, and it's just harder to put the field together. Okay, so I'm just going much longer than I anticipated, so I appreciate your attention. So Jerry said that 2 millimeter pupil was best. I think what he meant to say was that the eye's best resolution happens at 1 to 2 millimeter pupil. The best pupil for faintness, I would suggest, is 5 to 7 millimeters, based on that I can see these structures when my pupil is that size, and when I go up in power, they disappear on me. I'll talk about that more in just a moment. So, you know, this gets confusing. So I pulled out the 6-inch and 13-inch, put them side by side, and you can see that the eye does a pretty good job when you go up in magnification. As you shrink from 5 to 7 down to 1 to 2, the eye holds in there pretty well. Lowest power for the 13, yeah, it's a little better, more stars in the nucleus, but 6 inches not bad. Go up in power to the maximum of the 6-inch, pretty nice view. 13's better, but where the 13 really shines is at its highest power, where it's just a beautiful view of the sombrero. So the question then is, if the eye's best resolution is at 1 to 2 millimeter pupil, which by the way is what the eye's pupil is in the daytime, so is that a coincidence? So that's another talk. So what can we do to the sombrero to maximize the brightness completely? Well, what size telescope would have 300 power for its low power. So a larger scope or 150 to 300 power is low, is what you're looking for. So at a minimum, a 30-inch and larger would be the ideal scope to see the sombrero. Yes, you are throwing away potential resolution, and you can make it bigger if you want, but you're seeing the scope, the object at the maximum brightness, but at the resolution that's appropriate for the object. So now that being said, I don't want you to think that a standard scope is a bad move. It's not. I think an 8-inch f6f7 is a great choice, because I just showed you how magnification and the eye hangs in there really well. So if you want a scope that kind of does it all and doesn't kill your pocketbook, here's an 8-inch 7. I put in an all-azimuth mount before the Dobson era, and here's one of my first 8-inch scopes in a traditional Dobson mount. Get some appropriate eyepieces for them. They're really appropriate, powerful scopes. And you're going to see galactic cirrus with them. Maybe it's going to be pretty hard though, but that's okay. You're not pushing these scopes to do everything possible. And so I then come to this conclusion that you should actually have more than one scope. Here's the Tulip Nebula with the 6-inch, and you see all this wonderful stuff around here. It took me forever to draw it, but over here is through the 25-inch. I can see the Cygnus X1 shock wave, and it's, see these 3 stars in here? That's what these 3 stars there. A lot more detail. The wonderful view. It's not the same view. Which one is better? I like them both. And so it turns out, I guess in my life, I've had combo scopes. Up here is the 6 on top of the 30 with the 16 in front, and the background hidden under the plastic is my 10-inch. I used to have a 6-inch on a 24 back in the day. Here's a combo scope, a 6-inch and a 17 and a half mirror. That arranged the eyepieces side by side. I found that really cool and really useful to go back and forth really quickly. Here's a 4-inch eyepieces here and a 14-inch back and forth, pretty cool. So I'm a big fan of combo scopes. And sometimes I wonder if there isn't a way to get the, like through some type of flip mirror to go through the same eyepiece and focuser for multiple scopes. Okay, so I really appreciate your patience. I didn't mean for this talk to go quite this long, but here's the takeaways. If you take away anything from this, sketching is a great way to study an object and share what's seen. The eye is a marvelous detector. Fill it with light. Do whatever you can, but past that, use whatever magnification that is appropriate to make the object visible. At some point, magnification will fall behind and we'll get into the realm of empty magnification for that object, but it can be a really good substitute. The law of conservation of Entendu and the second law of thermodynamics rule. They explain really how scopes work along with the ray tracing. Stars are unresolvable because of the wave nature is just too coarse of the light. And so the mirror lens will produce airy disks. There's something to be seen with all scopes and magnifications, though the largest, faintest structures benefit from the highest Entendu. And consider a combo scope. Get 2 of them together. And finally, as Carl Sagan would say, somewhere something incredible is waiting to be known. And I'll paraphrase it for us amateur astronomers, something incredible is waiting to be seen. And so that's it. So if any of you are left or have any comments or questions, feel free.
Well, that was an excellent talk, Mel. Thank you very much.
Yes.
I love the quote too. One of the things I like about this group is that everyone is just still so in awe and excited about things, which is wonderful.
I think
Yeah,
I think Mel's taking us into a new realm here, and it's super awesome.
Yeah, I can't wait to watch this again. I didn't miss a single second of it, and I'm gonna have to see it. I really can't wait to rewatch this one. That was great, Mel. Thank you. And you didn't lose any. I think maybe 2 people dropped off.
Yeah.
Yeah. So Howard, are you still there?
Yeah, I'm here, and I have a question for you.
I was going to say, If you want real drawings, go see Howard's every couple, 3 months in Sky Telescope. I mean, he's given presentations to the British Astronomical Society. I mean, he's lectured them on how to do astronomy, you know. So the oldest astronomical association in the world. So Howard is the guy. If you want to see drawings and stuff, go listen to him. So anyhow, Howard, you were going to say?
Well, thank you for that. And that is selling yourself way short. But anyway, my question is when the slide where you showed the eyes focal ratio when it's fully dark adapted is 2.1.
Yes.
2.1. Do you see that there's a benefit to making your scope f2.1 to match the eye?
I do not. And that's because the scope and the eye are decoupled through the exit pupil or the Ramsden disc. So all you can really do is try to fill up the eye with as much light as possible. If there were 120 or 150 degree eyepiece, I would go for it because it would allow me to see even broader structures without having to shift my eye back and forth and move the scope back and forth. But I don't think that the eye as an independent afocal imaging system, that it has a focal ratio of f2.1 has any meaning or bearing other than that our eye can work as well as it does in dark skies at f2.1. We can't make telescopes that work at f2.1 despite all of our technological progress and wonderfulness. We still can't match, you know, the two of these things that we have in the front of our faces.
Oh, so you admit there are two.
Robert.
Finally, we get to the end and he
Perfect
admits.
segue.
So, Robert, what's the best way to double the end-to-do of an optical system? Tell us.
Well, you could stop at doubling, but you could go further if you want. And that's just opening the other eye and looking through both at the same time with that maximum exit pupil.
Yeah, so Robert Asamondi and Jerry Otian and Frank Supaski have all built binoscopes. I think they're beyond me. But yeah, that's the best way to double the end-to-do is go ahead and fill up both eyes. And it results in something called the binocular summation factor. And there's a big debate over, you know, where that comes from and what it does. But it is a marvelous view. And I do recall a little bit of a shoot off that we had at my place with Jerry and Robert and another really good observer there. And
Who was that?
the guy, the filter expert guy from Eugene.
Oh, Augie was there.
Yeah, Augie, right. But what we discovered and what blew me away was that Robert Asamondi's little 8-inch binocular scope, right? Really cool and everything, but like he walks up with it under his arm and he chops it down and he goes, okay, there. It was almost as good as my 25-inch on the number of objects. It was amazing, you know, what this doubling the end can do and our eye-brain computer would do. So, yeah.
Yeah, brains are cool. I mean, there's a lot of image processing going on in there that people don't really understand. I think mostly because, like, you know, I read everything that Mel's written and like applying these same things a different way than using a fast mirror is just to do two eyeballs. And so, you know, I think people have only just begun to understand how much image processing goes in the brain when you have two good signals.
You know, I can always tell when I've got my binocular scope at a star party, I can tell if people are actually seeing the binocular view or not by their reaction. Because if they just go, oh, that's nice, then you know that the images haven't really merged for them. It's when they go, holy crap, then you know that they saw it in stereo.
I noticed with when I looked through yours, Jerry, I think it was up at the Spur Road. It was almost 3-dimensional with 2 eyes.
It does look that way, and certain objects look even more so.
Wouldn't it be fairly stereoscopic, you know?
Actually, if you do the math, the distance, anything that you're going to look at with a telescope is too far away to actually show parallax, and so it wouldn't look three-dimensional really. But
Compared to looking through one eye, it's miraculous.
yeah, the thing is, your brain doesn't know that. Your brain doesn't know that it's too far away to show stereo, and so your brain processes it just as if it was a stereo image. And so, yeah, you see it in 3 dimensions.
Yeah, super cool.
One of the
Mel.
coolest things about binocular scopes, and you can really see this when you've been looking through a binocular scope for an hour or two and you go back to a standard binocular scope, is the milky smooth appearance of the objects in the binoscope. There's something about the eye brain compares the two retinas and goes, that's a little bit of false scintillation, suppress it, make it go away. And so you have this wonderfully smooth object. When you go back to a monoscope, you see this scintillation. It's like being in a room and turn off all the lights, get everything really dark, cover your eyes with a blanket or whatever, and you see these sparkles and scintillation going off. In a binoscope, that's suppressed. And yeah, that to me is one of the most remarkable aspects of a binoscope.
I'm assuming if a guy could make a good wide field binoscope, we'd be seeing even more IFN than what you're catching in your 30. Would you think that's the case?
I'm waiting for you to do it, Jerry.
Mine, I can get a field of view of about 1.5 degrees. That's the best I can do in mine.
Okay, so here's the question. I brought this up at our small observing parties. I can't help but wonder if there's a biohack, you could use with atropine and dilate your pupils. But I think that would not work because you still can't make your fovea any larger. And I'm kind of assuming that your pupils are as large as they're going to get when you're dark adapted. Has anyone tried that experiment?
Yeah, I have. And the problem is that your lens is not much bigger than your naturally dilated pupil. So if you over dilate, there's light going around the outside of your lens. It's not actually being focused on the retina.
Well, it's your fovea is where the photoreceptors are. It's a really small area at the back of your eyeball, and so that's something you can't change the dimensions. I was just curious if. So you say you've tried the atropine experiment.
Yeah, and the thing with that is what happened is everything just became washed out. It was
okay.
The contrast went down.
Interesting.
There's also an optical phenomena where these peripheral rays are coming in at an angle. And so they begin to lose optical effectiveness too. And there's a big debate whether that's 80 degrees or 100 or 120 degrees, but it does get worse and becomes really noticeable at some point. And, I just don't know. Much beyond 100 degrees if we'll ever see a true low power eyepiece that's more than 100 degrees.
Okay. Well, I know like some people also, if you ask Andy, he prefers really narrow fields, right? Some people really just want to, the light from the objects in the surround can be a distraction. And I don't know if it's actually the way now that I'm thinking about after your lecture, I'm thinking it's less of a conscious distraction than a light distraction. It's actually, you're seeing more scatter of the light maybe is that the function of field stops? Because if you wanted to, you could just take your eyepieces apart and remove the field stops and get you would get some aberration, but
don't do that. The eyepiece usually gets flooded with light, so don't do that.
Okay.
I must protest, by the way.
Okay, please.
The characterization that I like narrow fields of view is,
well, I'm sorry, I've heard you say it.
No, under certain circumstances and with certain telescopes, I like having the field stop in the view as a framing device, but generally I wouldn't say like 72-degree apparent field of view is that narrow. which is the field of view on the Precious on the,
Okay.
the Delos series.
So Jimmy Lowry has the 48-inch. He hates wide angle. He hates chroma correctors. He
Mhm.
wants to zoom in on that one galaxy.
Yep.
No distraction by other light. And there's something more profound too. You want a way to ruin your night vision a little bit after being out in the dark for an hour or two? Look up at the night sky. You know, it will saturate your eye a bit and set you back. So doesn't like wide angle eyepieces for that reason. But then he's a huge galaxy and galaxy cluster guy. So
Mm-hmm.
Yeah, that's true. You know, last night we had a really interesting example of that because we went up to the amphitheater because it was supposed to be clear, but there was a fog bank on the mountain. And of course, whenever there's fog up there, it gets really, 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 really dark. And so we waited it out about 45 minutes or so, and then finally a clear patch showed up, or a relatively clear patch in the sky, but it was nowhere near, you know, good transparency. But I could still see, because my eyes were so well adapted, I could see the double clusters so well, naked eye. It was amazing.
Another thing about last night that I noticed, Robert, was there was hardly any twinkling in the stars. The only star I saw that was twinkling was Cirrus. It was
Yeah,
really steady.
yeah, it was great seeing if you weren't in the fog. But
Yeah.
you know, I came home and there were no clouds, but with the light pollution, you couldn't see any hint of the double cluster. But that was amazing. I guess that was my point, is that when I got out of the car, it was pitch black, couldn't see anything. Much darker than it is when you can see the Milky Way overhead at that same site, which I never use a red flashlight when I'm there observing because you don't need it. Like your eyes instantly can work well enough. But last night it was so dark with that fog that there really was an extra level of dark adaptation going on, and it was pretty amazing. I kind of wonder, you know, how well one could see if you just sat in a box or something, you know, if you made sure. I guess that's why real observatories have domes.
yeah, and it gets really dark in a dome too, by the way.
Yeah.
The other thing, I think Howard uses an eyepiece shield. Jerry, do you have an eyepiece shield or?
I don't have an eyepiece shield. I sometimes cup my hands around the eyepiece.
Yeah, I cup my hands too, but
I have a shield that I use maybe 10% of the time, mostly for neighbors' lights.
yeah,
Well, I know
they're
with
bad.
with the solar stuff, you guys put like sometimes a towel or something over. I would imagine that would do the same thing, right?
Yeah, they make an astronomy jacket. It's like a hoodie with a really big oversized hood that you can just lay down over the eyepiece, and those work really well.
I've used the hood when I'm looking for really, really, really faint stuff like the flat galaxies and some of the Hicksons and such. And you just have to make sure to bunch it up so that you're not seeing the ground or
There you
anything
go.
else.
Either Randy's either medieval or demonstrating the hood.
Annette made these for me. I have two of them, one for the winter because it's warmer, but this really works well too, to just zip right down around the eyepiece. I don't know if you can see what I'm doing, but
Hey, Mel, why don't you unshare your screen so our images get larger? There you go. Now, Randy, where'd you go? There you are.
so you can get this right down around the eyepiece and just block out everything around. And this is the lightweight one for summertime, and it's Velcroed at the bottom, so I can just pop it off. And then she made me a heavier one that's more insulated for wintertime.
Plus, it works really well for the secret astronomy rituals that we conduct.
Oh yeah.
I swear, Andy, you always give away
Andy,
these
you shouldn't
secrets.
say that because some of our new members are going to wonder what's happening.
Oh, well,
Or
We have
maybe
to-
you should say that.
yeah, they gotta know what they're getting into.
I'm like, what, almost 4 years in and I still don't.
I don't think anybody really does.
Well,
Can I-
I learned from one of my first things that I've mentioned this a few times. One of my very first EAS meetings was if you're comfortable, you're going to see more. You're going to see better. And I also think if you can just get rid of all the ambient light around you and just look at what you're looking at, that's almost about the same too.
Yeah, it really works so well. My eyepiece baffle basically blocks light 270 degrees. You can only see light coming up from the ground. And that darkens the eyepiece view tremendously. A winged eye cup on the eyepiece, that works almost as well. The hood works great. The only problem I have with the hood is that on, during this time of year, it's really easy to fog the eyepiece with the hood. But they work fantastically well otherwise. Cupping, that works too.
The R sky system, heating the eyepiece up, it really works well to reduce.
Oh, there you go.
Yeah.
That's about the only electronics I use when I'm out is the dew heater for the eyepiece, just to keep it from fogging up. So yeah,
well worth the money, especially when it's really dewy.
Eureka Ridge.
So can I ask a question? I live in Central Oregon, so what is this fog and dew that you speak of?
Yeah.
Go away.
Up yours.
I'm going to stop recording real quick, okay?